Hi, this is Ms. Fitzmaurice. This video is an explanation of the problem on page 24 on your Unit 5 packet. So this problem says, a pendulum consists of a small object of mass m fastened to the end with an inextensible cord of length L. Initially, the pendulum is drawn aside through an angle of 60 degrees. So we know this angle right here is 60 degrees. And eventually, the string over here is going to be burned and it's going to swing aside. Okay, in part A, all it wants us to do is draw a force body diagram identifying all the forces acting on the object while it's held by both strings. Okay, so in this situation, we have a tension force from one string. Okay, we have a second tension force from our second string, and then of course we have gravity. And that's all we have. In B, it asks us to determine the tension in the cord. It means this cord right here before the string is burned. Okay, to do this we need to use forces, of course. So we're going to write out sigma Fx equals max and sigma Fy equals may. Okay, in the x direction we have right minus left, so that's T1 minus the x component of T2, so that is going to be T2 sine 60, and because it's held still, A is 0. Okay, remember we're solving for T1 right here. Okay, so we can write T1 equals T2 sine 60. And you should know that sine 60 is about 0.86 because it's one of our special angles. In the y direction, we have T2y minus Fg. Again, this thing is not moving, equals 0. Okay, now we have T2y is going to be adjacent to that 60, so that's T2 times cosine 60, which is of course 1/2, minus mg equals 0. So I'm going to take this to the next page, but we have these two equations right here. Alright, so these are our equations. Of course, we want to solve for T2 over here and substitute it in right here so that eventually we can solve for T1. Okay, so we know that the cosine of 60 is 0.5, so we have T2 times 0.5 is equal to mg. And they don't give us a number for m, they just say m. So we have T2 times 0.5 equals mg. I'm going to divide both sides by 0.5, and I find that T2 is equal to 2 mg. Now I'm going to take this and put it in for T2, and I have T1 is equal to 0.86 times 2 mg. T1 is equal to 1.72 mg. And actually, reading this again, I think we were actually only supposed to solve for T2, but we did that as well. Okay, now in C it says, show that the cord strong enough to support the object before the string is burned is also strong enough to support the object as it passes through the bottom of this lane. Okay, so we have a tension. Now that this thing is just held by one string, at the bottom we're going to have this for a force body diagram, T2 and mg. And because this thing is swinging down, we know that and it's swinging in a circle, sigma Fy equals MAy. Now that it's swinging in a circle, Ay is equal to Vt squared over r. Now you may say, oh, we don't have any kind of velocity. Actually, we can find it using conservation of energy. Okay, so what I'm going to do for part C is we're going to solve for T2 in terms of forces, solve for Vt in terms of conservation of energy, and then plug it back in. Okay, so in this case we have T2 minus mg equals mvt squared divided by r. And r in this case is just going to be the length of our string. So I'm going to replace that with L. Now I can solve for T2, and I have T2 is equal to mvt squared over L plus mg. Now I want to find something to put in for Vt squared. And to do that, I'm going to use conservation of energy. Okay, so if I look at this, so this is the pendulum swinging down. This right here is going to be my time 1, my P naught, and this is my time 2, or my E. I want to set this height right here equal to 0. Now what I need to find out is what this height is so I can plug it into gravitational potential energy. And the way I'm going to do that is that I'm going to do a little bit of geometry. So I'm going to get rid of these things. Okay, I know that this angle right here is 60, so this length right here is L cosine 60. Okay, I know that this whole length is L, and what that means is that this distance has to be L, the whole length, minus L cosine 60. Okay, so that's my height. I have height is 0, and then I have height equals this L minus L cosine 60. Okay, so looking at this picture, at the beginning our object is at rest. It only has gravitational potential, so I have UG naught. At the bottom it has no gravitational, but it does have kinetic, and the V inside of that kinetic will help us find Vt. So we have UG naught, which is mgh, is equal to 1/2 mv squared. And I'm going to put a T because this thing is moving around in a circle. Now, I know I can get rid of my m's. Oops, that was supposed to get rid of the m, not the factor of 1/2. So I'm getting rid of my m's. And for my h, I'm going to go ahead and put in g times L, and I'm factoring out an L, so I get 1 minus cosine 60. And that's equal to 1/2 Vt squared. Okay, now what I can do is I can solve for Vt. Okay, so I have 2gl times 1 minus cosine 60, and remember cosine 60 is 1/2, so 1 minus 1/2 is just 1/2 is equal to Vt squared. Okay, so I have 1/2 right here times 2, and those will cross each other out. All I'm left with is GL equals Vt squared, and Vt is equal to the square root of GL. Now I'm going to take this and I'm going to put it back into my forces expression. Okay, so just as a reminder, I had T2 equals mVt squared over L plus mg. Alright, so I'm going to take Vt, I'm going to substitute it in right here, and I end up with T2 is equal to m Vt squared over L, which is GL, because I'm squaring square root of GL, divided by L, plus mg. You can see that these L's go away, and I have T2 is equal to 2mg. Okay, since T2 was 2mg before, the rope is strong enough.